G'day there, you're watching the Aussie BIM Guru. Today I've got a pretty exciting video to share with you, and actually just a little mini-series on generative design, which is becoming more mainstream at the moment. One of the reasons is that Revit 2021 now has a generative design tool, as probably most of you are aware. So we're going to cover it today in a video demo. So I'd like to firstly thank Jacob Small for helping me through understanding this tool and working through a few bugs and issues I needed to resolve to get this to work. He actually manages the product as well. He's one of the product managers at Autodesk. Anyway, in this video, so I'm going to cover a few things. So what is the tool? How does it work? How can we build a script to use in generative design using Dynamo? So we're going to build a full example from the ground up. We're not going to use one of the Autodesk samples, which is what a lot of videos are doing, unfortunately, which doesn't really teach you a lot about the tool, really. And we're just going to run an actual study and look at the results. And I'm just going to give you my thoughts at the end. So if you just want to know what I think of the tool, feel free to jump to the end. But otherwise, we're going to build a script then. We're going to build a study. So the files for this will be on GitHub. So if you want to save yourself a little bit of time, feel free to jump over there and download my files. So Revit 2021, you might have seen the new marketing video that they've released, which shows the generative design tool in action. I will talk about their marketing at the end and what I think of some of the ways they've marketed the tool, some of the authenticity and some of the issues with it, but that's okay. One of the really big things to note here, and one of the biggest complaints about the tool, is that you do need Revit 2021 as part of the AEC collection. So if you're a student with a student license, you don't have access to this tool, unfortunately. In general, the principle of generative design is quite straightforward. We're essentially taking a bunch of inputs, usually numbers or something that numbers can drive, and we're randomizing and shuffling these values in a range. What this does is gives us the ability to influence an algorithm many times over and over again, and we generate multiple studies using this algorithm. And then we can collect the goals or the measurable components of the script, so how successful was our study? And we can use these goals to analyze and optimize the best options out of our studies. And essentially this is the basic gist of generative design in general, but it's also how our script is going to work today. So how does it work? Well, we generate multiple studies to find the best outcomes. So there's going to be 3 ways we can do this using the generative design tool in Revit. So the first one is randomizing. So we can keep running the study in multiple sessions over and over and over again, and then we can filter through the outputs at the end and just find the best result. We can also use a method called optimize, which generates multiple tests. So it might run it 3 times each times 4 seeds. So we might get 12 total tests, but we're only going to see the most successful test out of each batch of tests. So this way you don't see the really bad results. You only see the ones that are almost the best of the best, and then you find the best of the best of the best out of them, essentially. As well as that, you can do what's called a cross product, which is where we generate every single possible outcome so that we can fully analyze the results. We don't tend to use cross product because it's pretty slow and it does a lot of results. But if you're really needing to get to the absolute best of the best, this is the way to do it. So we're just going to demonstrate how to actually use this tool. So I'm going to actually build a Dynamo script in a Revit model to generate a building on a site, and we're going to measure a yield based on the view aspects of this particular site. We could use a technique called isovists, which are quite advanced, but unfortunately I found that in Dynamo they're a bit slow, so I'm not going to use them in this case. I'm going to use a raycasting method instead. But let's just jump into Revit, and I'll just show you my sample model, which will be on my GitHub. So essentially all this model has is it has a property line, so it has a property boundary, just 4 sides. My site is approximately 150 meters by 100 meters in this case, and it's just a rectangular site, so nice and easy. As well as that, I've just modeled a generic model piece of context. So I have some buildings, they're just of different heights. Now obviously these are very simplified buildings. Usually a city model is going to be more complicated than this. There's going to be some issues in Dynamo if you have a really dense, complicated city model, because Dynamo isn't really that good at handling heavy geometry, such as a advanced high-resolution city scan. So in this case, I am using a pretty simple representation of a city, and usually if you were working with a city model in Dynamo, you'd probably have to go and remodel it or simplify it using a tool like Rhino. But we're just going to work with a simple model. So I'm going to go to the Manage tab. It's important to note the generative tools are here. We're going to look at this at the end when we generate our actual study, but for now we're going to build a Dynamo script. So I'm just going to jump straight into Dynamo and get started. So I'm just going to resize my window so that you can see my beautiful banner. Okay, let's just resize. Cool, so we fit and we fit. Cool. All right, so we're just going to go new and we're just going to get started. Now, I haven't really got many packages at the moment because I've been doing some training for a website. But what we need here is we need this generative design package that comes with Revit. So I did have some issues with this component package at first. So make sure you've upgraded your generative design tool to the latest build, because essentially this package should live in your app roaming Dynamo Revit 2.5 packages folder. And this contains some of the key functions that allow this tool to work. So we're going to start just by collecting our property boundary. So we're just going to get a select model elements node. And I'm just going to go and select my property boundary in floor plan. Great, so we've got our input. So this is an input. So we do need to tell Dynamo that right-clicking and saying is input. In this case, I like to call my inputs with an in, and I'm just going to say in boundary, because we will see this in the interface in our generative design tool. So if you can identify it as an input, it makes it easier to audit and verify your script. Okay, but let's get element.curves. So we're going to get the curves of this element, and we should expect to get our property boundary line, hopefully. In this case, it looks like we haven't yet. So what I might need to do is make sure I've got my full property boundary. Yeah, so at the moment I didn't have the full property boundary line, I just had a segment. Now if we get these, we should hopefully have, there we go. Now we have 4 lines. So let's just zoom fit. It's a pretty big site. What I might do just in anticipation for it being a big model is just go to settings, geometry scaling, extra large. So what we're going to do now is just do a polyline by joined curves. So, or a polycurve by joined curves. Just to make this one curve. And I'm just going to turn off my previews as I go. Now what we need to do now is store this in our script using a data remember node. So in this case, our geometry is going to be stored inside this node when our study runs, and it can keep using this geometry over and over again. So it's going to save some of the load that you place on the script, and it's going to allow your script to work. So that's pretty important. So we could generate a preview for this. What I usually like to do is do a geometry color by geometry color node. And I'll take my data remember, and I'll just get a color by ARGB in this case. And I'm just going to generate a red boundary. So I'm going to make 255 and 0. And I'm going to get 255 for my alpha, and my red, and 0 for green and blue. Now if I stop previewing my site boundary, we should see we get a red preview, which is pretty helpful. Now what we're going to do is inset the boundary of our site, and we're going to inset it by the width of our building that we're going to generate. So in this case, I'm going to use a curve offset node. So actually we need to use curve offset, not polycurve offset. And we're going to specify the amount we want to inset by. So what we need to do now is generate an extra input. So this is going to be one of our first randomization inputs. So we're going to make it in this case, a number slider. Actually, we can make it an integer slider maybe. In this case, we'll just make it, we'll make it an integer slider so it has less values to work between. So we're going to work between a range of 15 meters and 50,000 meters. So millimeters, sorry. And we're just going to call this in, and we're going to use this to control the width and the depth of our building that we create. Because a square building is a little bit easier to assess because we can offset our boundary by the same distance on all sides. If you were generating a building that had a two-dimensional size that was different in both aspects, you'd need to also control the inset of your property boundary to make sure it never overlaps by the relevant aspect of the building. What we'll do is just generate a code block, and we're just going to call this length times -1. And we're also going to divide this by 2, because this is going to be the inset that we want to push our site boundary in by. Because we're going to generate a building anywhere within this boundary. So the building could be generated centered upon the boundary. So we need to make sure it never goes over the boundary of the site. And you could obviously apply additional tolerance to your boundary if you needed to. Okay, so we've got our inset boundary. What we're going to need to do now is turn this into a surface. So we're going to make a surface patch or by patch. Now we have a surface. So we can actually assess this surface by a UV coordinate now. So we need 2 more sliders. In this case, they're going to be number sliders because they're going to be less than 1. So we need a slider number slider. There we go. So we're going between 0 and 1, and let's just go with a step of 0.01, so that we have a decent amount of range to work between. We've got two significant figures. So we're going to call this in_u, and I do need to go back and just make sure I made this an input as well. And likewise, we need to make this an input, and we're also going to make a v coordinate as well. So we have u and we have v. And in this case, we're going to generate a point at parameter. So we're going to generate a point on our surface at a specific UV parameter, so UV. And then as these change, we go to a different point on the surface in our site. So you can see here that at its extreme, it's at the edge of the site. So as these randomize, we're going to change the location of the building on the site. So this lets us test a lot of positions that we can place our building at. So now you can sort of start to see this playing out in a generative aspect. So what we're going to do now is we're going to generate a plane. So we're just going to make a plane by origin normal. And we're going to generate it at this point with the normal of the z-axis in this case. And the reason we're going to do this is because we're going to make a rectangle by width and length, which needs a plane. So in this case, we're going to make our plane that point, and we're going to make the width and the length equal to this variable back here. And now, as this moves around our site, we can see that it will never go past our boundary, and as it increases, it will never go over our boundary as well. So we've generated the base of our building at this point. Now what we'll do now is generate a method where we can use to ascertain the height of our building. So I'm going to make the height based on a maximum volume that the building can be. So there's a lot of ways you can constrain this value. Usually you'd want to work with a floor area, but it's a little bit more complicated to do that. So to save some time, I'm just going to use a basic formula. So I'm just going to turn my values from millimeters into meters, so that I can assess my width and my depth on the basis of meters. I'm then going to say that my area that I'm generating for my base footprint is L by L, because it is essentially the width by the depth. So now we have the square meters of our footprint. Let's say that our limit for what we're allowed for our height ratio is 50,000 square meters. We can then say that our height is equal to our limit divided by our area times 1,000 to turn it back into millimeters. So now we can generate a formula that connects our width and depth to the height of our building. So as our building gets bigger, it gets shorter. So we do have a consequence for making a wider, bigger building in this case. So obviously the higher the building is, the more constrained we'll need to make the footprint of the building, because we obviously have area constraints that we usually work to, like GFA. So that we're going to use that in this case. And I might just actually save my script before I forget. We don't want to forget to do that. If we crash, that's bad. Okay, so what we're going to do now is generate a solid. We need to generate an actual building form. So we're going to extrude as solid. And we're just going to do it by a direction and a distance. So we're going to take our rectangle. We're going to move in the z-axis direction by our height. So now we've generated an element that will essentially grow on the site, and it will also be able to be moved around the site by our generative study as these three inputs change. So you can start to see the study taking shape. We're obviously going to keep analyzing just a little bit. In this case, I'm just going to make sure I'm not previewing too much. Okay, so this is our building. So at this point, I might just create another geometry preview. So I'm just going to copy these three nodes to here. And I'll just override that geometry. And red's a little bit of an aggressive color. Let's make it blue instead. Much nicer. There we go. So now our option is blue, so we can turn off our extrusion. Okay. So the next thing we need to do now is we need to generate our views or our tests for whether we can see past the site at certain points. So what we'll do here is we'll also just check off our height. In this case, we want to watch our height. We want to see what height all our options have. So we need to make this an output. So I'm going to use a math floor node just to round this to a nice even number. So you can see now we get at least a 8.2, 8.24. It's a little bit more friendly. And in this case, we're going to get our output. So in this case, we need to make it a watch node. So we're going to watch our output. I'm going to right click it and go is output. And I'm just going to call it out_height. So now we can watch this as our study generates more options. Okay. So what we need to do now is actually translate our point that we're detecting our views from. So in this case, I'm going to be using a geometry translate node. I'm going to translate by distance and direction. So my geometry is my point that I'm generating my study from. So let's just temporarily hide this. So what we need to do in this case is we do have to build up a range of values to divide our building by. So in this case, I'm going to be generating a direction and a distance, but I'm going to generate a range of distances instead. So what I'll do is I'll generate a range. So I'll say between 0 and the height of our building with a step of 3,500. I'm also going to generate a z-axis vector just for convenience. So I'm going to type in vector. I'm going to type in z-axis, bracket, bracket, semicolon. And I'm just going to go collect my building height. And we should get a range of numbers spaced between the height of our building. So these are the floors of our building. So what I can do, now I can make this the distance, and I can get my axis, my z-axis. Now we have points at the center of our building for every floor in the building itself. So we can use these to generate our tests. So what we're going to do now is we're going to count the number of results we have. How many floors do we have? So we just need to count this range, and we can see now we have 24 floors. So we're going to generate a range essentially for the value of our yield. We might actually just, we'll generate the full formula because I've got a little interesting formula I use here. So let's just say, what's our ground floor value? So what's our initial value at the ground floor for one view that we can see through? Let's say it's $100 or $100,000 or $1,000, whatever number you want to make it. And as it climbs up the building, how much more valuable does that view become? Because we know the higher you get, the better the view, and the more you can charge for it. So let's just call this the climb value. So as we go up, we're going to increase this value. So we need to build a range at this point. We're going to say, if we start at the ground floor value, and then we go ground, and then we're going to say plus, we're going to say the climb value, well, the count value, sorry, -1, times, in this case, the climbing value, so CV. And we're going to go up. Now we need to go fix that. We're going to go up in increments of the climb value. So we're going to go from ground. We're going to input our count, and we're going to put our climb value in there. And now we get the values at each floor for a particular view. So we now have the value per view. So we're going to use this as well. What we're going to do in this case is just generate some lines. But first we need to rotate a vector that's pointing up north by each specific angle of view that we want to test. So in this case, we're going to get a vector.rotate node by axis and degrees. So in this case, my vector I'm going to start with is just the y-axis. I'm going to go vector.y-axis. And then I'm going to be working at the axis of the z-axis, so pointing up, so that as we rotate it, it spins around the z-axis. And I'm going to work between 0 and 350 with a degree of 10. That way we don't generate two views at 0 and 360. So now we should get a range of angles to work at around this angle. So we're going to go vector, axis, degrees. And we should get a set of 36 vectors spinning around with an increment of 10 degrees. Now you could increase this if you wanted to have more views. You could make it 5, you could make it 3. It just depends on how accurate you want to be. So I could use an isovist here. I'm just going to work with a basic raycasting method instead. So let's just do line by start point, end point, by start direction length. So we're going to do line by start point direction length. So we're going to start at those points. And in this case, we're going to be working in the direction of the vectors. For the length, it's up to you. I'm just going to make it a pretty big number. So I'm just going to make it 1,000,000 at the moment. Now at the moment, it's not working the way we want it to. For each point, it's lining up a vector to each one and generating a line. We don't want that. We actually want to work a little bit more smart. I might actually just make these a little bit shorter. Anyway, what we're going to do is we're going to apply this on a cross product basis instead. So check it out. Now we get array for every single point. It's still a bit big. There we go. That's better. So it's pretty intense. We've got quite a lot of views. Obviously, the further away you get, the less accurate you're checking your view, because in the middle, you've got a lot of viewpoints being checked, but then you're missing out on a lot of in-between views as you go. So it's up to you how finite you want to work. we're just going to turn off this preview. And in this case, we're just going to check if this intersects with our site geometry. So in this case, we're going to get a geometry does intersect, just to query it. So we don't need to find the point that it intersects at. We just need to check if it intersects in the first place. What we're going to do now is we're going to get our site context. So we're going to get a select model element, and we're going to go get our site context. So we're going to select this. We'll just move this back out. So now we have our site. So let's call this in context. And I'll just right click and make it an input. I then need to get the element geometry. So this should give me my solid geometry. Now at the moment we'll have a whole bunch of solids. Let's turn them into just one element so we can clash them. So we're just going to create a union of solids. So now we should just get one solid that represents our entire site. Much easier. And what I can do with this is just get a data remember node that we can use to store this geometry, like we did with our site boundary, so that now it remembers this element. And we can just turn off the preview for this, and we can just get another geometry preview for our site. And we can just preview this instead. So I'm just going to turn on these, turn on my buildings preview now. And we can just change the color for these. Let's just say we want to make it 125. We want to make it gray. So we'll just make red, green, blue, all gray. Let's make it a bit lighter. It's a bit dark at the moment. There we go. And now we can see our site's preview. Let's just zoom in a little bit. So now we can see our study really taking shape. So what we're going to do now is we're just going to check if our site geometry, as other, intersects with each row. And we should get a whole list of true and false outcomes depending on whether the lines intersect with the site geometry. What we're going to do now is we're just going to count the number of false outcomes, because these are going to be all the successful views that are obtained in each list. Now we do need to work at level 2, because now we're just getting all the falses in the entire list. If we work at level 2, for each level, we actually take an assessment of how many rays. And as we can expect, the higher we get, the more amount of false outcomes we receive. Now what we can do with these is multiply them by the value of the view which we obtained. So we can take those numbers and multiply them by the value of each. And then we'll get a yield per floor. And what we can do with this is just sum it to our overall yield. So we'll take all those values and we've got an overall value. So now we can see that our yield in this case is 54,875. If we go and change our site, let's go and make our building a little bit shorter and a little bit taller. We should expect that we'll get a different yield value, which we can see in this case we have. Let's go and just decrease our site, and we should expect a lower yield. And of course we get a lower yield. So this can be our fitness measure for our study, which is really powerful. So what we need to do now is just get another watch node, and we're just going to watch that value, and we're just going to call this out, and we'll just call this yield, and we'll right click and make it an output. So at this point we have a full generative study ready to go. We have some inputs, we have some outputs, and we have some geometry that we're going to use. So I'm just going to save this, and what I'm going to do is go up to here to this Generative Design tab, and as long as you have this package installed and available, you should see this tab. So if I go to export for Generative Design, and we'll just give it a description. Let's say, let's hope this works. Now you can give it an image as well if you want to give it a little thumbnail to tell your users what the study does. As well as that, you can keep the inputs. So if you're going to run the study multiple times, you may just prefer that the default values are retained. So in this case, that's the site geometry, and also the geometry for the property line. I will in this case. So I'll export my study. It gets saved to your documents, typically in an AEC Generative Design folder. So it is important to understand the structure of this little folder. So we can see now we've got a couple of things. We have our Dynamo script, and we also have a dependencies folder. This dependencies folder contains any definitions and packages that relate to your script. So in this case, we have the data remember node in this package. So it's made a copy of this package. If you have any custom packages, you will need to make sure that they're present in this folder. Okay, so what we're going to do now is just close Dynamo, and hopefully it works. So I'll just go to 3D. I won't see my results in Revit, so it doesn't really matter. We're just going to go to create study. and this should boot up the Generative Design tool in Revit. There we go. So we've got our demo scripts and one that I was testing before. So we can just give our test a name, testing. Now I could use an optimized study. I find the optimized study doesn't really showcase the dynamic nature of generative design because it gives you the best results it can find. So most of your results will be quite optimized. In this case, I'm just going to use a randomized study instead. Now you can see that I've collected the elements automatically because they're cached. Well, I could still go and collect different elements just by clicking on select and sourcing different elements. So you can build your scripts to be quite dynamic if you want to. As well as that, you can choose what you're randomizing. So I can see that I'm working between these ranges because I used a slider. So in this case, I have the ability to set that limit. Let's just say in this case, we're going to let's do 50 solutions. Let's do a decent amount. And the seed can be used to repeat the same results. So in this case, I'm working at a seed of 1. If you wanted different results, you'd need to change your randomization seed. So now let's just go generate. And it should get started. So I've got a study I did before, but let's watch it go. So at the moment it's at 0, but it should go pretty quickly. Check it out. Here we go. Our results are starting to populate. Sometimes they seem to get started and then they sort of stagger a bit. But we can start to see it happening. Now at the moment, most of my results are pretty short and fat. But we will be able to look through and we will see that some results aren't quite going to be like that. Some are, some won't. And as we go up, we'll see that our building starts getting taller. So it's being sorted by height at the moment. Now I could sort it by yield as well and just look at my most profitable outcomes. So I can see that I've got some pretty profitable outcomes and some pretty weird building shapes, to be honest. But the thing that I really like about the tool is this dialog down here, which lets you filter your results. Let's say I only want to look at certain heights and see what happened. So I can see if I have a bigger width or depth, I can sort of follow my values and see that they're not really going that well. So I can see that I can move through my results and it starts to show me the data pathway. So I can see as I reduce my width and my depth, as we expect, we're going to start getting some better heights and some better yields. You can also just really focus on certain things and say, well, this is funny. I've got a really small width and depth, but I've got a really bad height. And I've also got a pretty bad yield as well. So I can see that in this case, there are certain positions on the site that aren't very desirable. So I can see here that the reason why this did really badly is because it's right up against a building. Obviously, you're going to get some really bad views if you're just abutting another building. And likewise, if we look at this one, I can see that I'm not in an ideal position. I've got quite a lot of tall buildings that I'm getting some views blocked by. So you can click and drag around and really have a look at these studies and start to make educated assumptions and ideas about why your study might be giving you the results it is. And you can see sometimes your filters won't pick up anything. As well as that, I can just look at my best results and say, let's see my best results. And obviously it's going to be a spaghetti tower because I'm obviously going to maximize my views when I have no sight around my building. So I can start to take out some of those more unrealistic results and sort of start honing back down on some results that are probably giving me a more logical outcome. So I can see in this case that if I'm in this position of the site, I'm getting a pretty good view aspect because I'm peeking around that corner. Likewise here, I'm somehow just avoiding a lot of my peripheral buildings. So I can start to really filter for logical outcomes. And surprisingly, I can still get an okay yield in some of these areas on the side. It's surprising it thinks that one's a better outcome. I guess we are actually in a pretty terrible portion of the results. So we really can start filtering and seeing what sort of things make those results better than others. So hopefully that gives you a better idea of the possibilities of the tool and how you can set up your own study. But I guess I'll give you my thoughts on the tool as well. So my thoughts vary on the tool. There's what I call the good, the bad, and the ugly. Now, there's not a lot of the good listed here, but the good things are very good. So there's a lot of weighting on these. So I think the tool has a lot of potential. Just like Dynamo introduced everyone to visual coding that wasn't using it already. To be fair, Grasshopper had already done a good job with that. But it exposed Revit users to something new. And the Generative Design tool is going to do that as well. As well as that, the user interface is brilliant. I love the filtering tools that they brought over from Refinery. I think that they're really easy to use and understand, and they're probably something that a designer will need in order to trust generative design, because they still need to make informed decisions about the outcomes. Now, the bad. So the bad isn't necessarily the terrible. It's just some things that I don't think are that great that maybe they need to think about over at the development team. So I think that there are more examples needed, and hopefully things like what I'm doing will contribute more ideas towards how the tool can be used. Because if people see these types of studies, they might go, hey, we can actually use this, we need this. Some of the studies that Autodesk generated aren't really that useful. It's how to fit a whole bunch of desks on the same angle in a room. Like, for example, we just don't do that usually in most projects. Is it better than other solvers? So, Grasshopper has a lot of solvers already available. And there are other programs like TestFit that already do a lot of generative solving for us. So is this really the right time? I'm not sure. Maybe it's too late to the game. Maybe it's just in time. We'll have to see how it goes. As well as that, I really wish that they'd market the results and the tools a little bit more honestly. They are over-exaggerating the speed in their marketing videos. So for example, I hate to nitpick, but I was watching the trailer, and in the workspace layout study, they press play, and it's 1 out of 10,
the distance
and bang, 10 out of 10. Now, it doesn't work that fast. Let's get real, guys. Come on. It doesn't go from 1 to 10. You saw that it took a little bit of time to generate the study, so that's a little bit misleading. I can't actually see what the timestamp is, but I'm sure if you could see it, the time would change. So let's just mark it with a little bit of honesty. Let's not mislead the industry into having unrealistic expectations about what generative design can do and how easy it is to do. Don't lower the benchmark just to get your marketing up, right? Anyway, that's just my opinion. And I guess the ugly. These are the things that I think are actually problems for the tool that are going to be challenging for the team. And I think they really need to keep these in mind. So the ugly is that geometry processing in Dynamo is still an issue. So I have a script that can use isovists as well, but it can't really handle more than about 10 floors at the same time. It will just crash and spin out, unfortunately. So whereas in Grasshopper, for example, you could do that so quickly. So there is just the issue with the geometry limitations of Dynamo and Revit versus other programs. And this is really becoming quite relevant because of a tool called Rhino Inside, which lets us run Grasshopper and generative solvers inside Revit. And we've been able to do this for a little while. Now, in my opinion, Autodesk needs to collaborate with this team. There's so many opportunities that this tool provides, and whilst it's not developed by Autodesk, I really think it needs collaboration. I'm trying to collaborate with them as just an everyday person using software, but I think Autodesk really should do it as well, because this tool does offer a lot of possibilities. Anyway, I digress. So in a future video, the first one I'm going to be looking at Galapagos in Rhino Inside in Revit as an alternative approach. And we'll see a different approach, a different user interface, and a different speed of generation of options. But it's going to be a little bit different to what I've shown you today. So there'll be some good things and some bad things about this alternative approach. And as well as that, I'll do a quick video where I just put them side by side and sort of show how they work, because I think this will be a really good video as a business case or just a marketing perspective that people can show to their peers and to their business, just as an example of two of the options out there. But just a reminder, my files are on GitHub, so feel free to go there if you need them or if you'd like them. And thanks for watching today. Thanks for those that made it through the presentation. And hopefully this shows you an option you can use in your generative studies. And it gives you more of an idea about the possibilities of the tool and how it can work. And if you have any questions about what you've seen today or studies that you're working on, feel free to comment and leave down below, and I'll get back to you. But thanks for watching today. If you're not already following and subscribing, feel free to do so. I make 2 videos a week typically, and I hope to do so for a while. And I look forward to seeing you in future videos. Thanks. Take care. Bye.